soggy, and I went around to various places a couple of years ago with the discourse. And you go to places, and they'd be showing results of 3D inversion, magnetic alert data, or something like that, right? And you just take one look at it and you're like, there's no way the Earth could possibly be like that, And so you talk to them and say, well, fit the data. Well, what do you use for program? Probably don't use this 3D inversion code. And then you start talking to them, and your first initial reaction is like, okay, I think this person's kind of interesting because they've got all the words. They've got the data misfit and the regularization, the Tikhonov parameter. So they, at a high level, they can talk. Okay, and it sounds like okay, they're perfect. But then you start asking questions a little bit more underneath, and you realize like, there's no real idea about what is going on, and that's the kind of thing that can lead to an inaccurate result. Getting a picture out is not a big issue. Getting the right picture out is a big issue, and that is the details. Every step, and that's why you come into workflow, and you need to be really critical of every step, what information you're putting in, and how it's going through. So what I'd like to do now is, since we've done the linear problem, let's go to the nonlinear problem, which most problems are, even like the linear problem when we decide we want to do positivity. So we're going to first look a little bit at the forward problem, and then nonlinear optimization. And then we're going to do sensitivity example. How many people? There's certainly been a couple of people that have been involved with DC resistivity. Could you raise your hand? Just how many people have somehow been involved with a DC resistivity survey or interpretation? 1, 2, 5. Okay. It's one of the longest-lived, most robust electromagnetic methods, and we're going to show it. So a nonlinear problem. So we're still going to set it up in the same way. Here's a misfit. For the linear problem, we were able to write that D was equal to just some matrix G operating on M. We had our quadratic regularization, kind of looks like that. And we could just solve this in one step. So we still had this parameter beta to deal with, but basically, we're able to solve it in one step. So the problem, however, becomes nonlinear if any of the following happen. For instance, if this forward mapping operator that you've got is nonlinear, it could be nonlinear because this could be changed. We've got 2 norm here, but you could make that an L1 norm or something else. So that could be make it nonlinear. And then this quantity here, your phi m, if that's a non-quadratic function, that also changes things. Any of those alterations means that you now have to deal with a nonlinear problem. So this is, as I said, that was our definition of the nonlinear problem. If we took this and it did not equal that, then we say it's not. Examples? Seismic problem, except for that straight ray to rock radiation problem. But if you have curved rays or something like that with the Penderon velocity, that's wrong. Maxwell's equations, DC resistivity, and yeah, irrespective of that, we're going to still solve the problem. So when we have these examples in here, we're going to have to take whatever partial differential equations we have, and we're going to discretize them for the forward problem. And then we're going to have to iterate for the inverse problem. So let's just start kind of simple and think about just a single variable x and some function f of x. So if in the first case, let's suppose f of x looks like this. So that's actually quadratic, and it's got a shape that looks like that. And if we found where the gradient is equal to 0, and where the curvature is positive, then we've got a minimum. And that's easily solved. Solution X solution exists. But suppose things actually look like this. So something that's got squared, cubed, 4 powers, right? That function is no longer quadratic. Oops. Yep, and maybe it kind of looks something like this. So in one dimension, either that or not. There's a couple of places that have gradient equal to 0 and positive curvature, so that would satisfy our condition of minimum. But there's clearly better minima than others, so this one is perhaps the smallest of all of them. So that's kind of like a global minimum, and this we'd often refer to as a local minimum. When you get to problems like that, that can be really challenging because things will depend upon where you are. This is how we're going to start. We're going to actually kind of work with a starting position someplace that is wherever, and then we're just going to basically try to find the nearest local minimum. Trying to do global problems in which you find, the global minimum of things is a whole entirely different process than anything I've done. So how do we do that? So suppose we had something kind of look like this. Then what's the procedure for getting here when we're starting here? So we're going to start here. And so let's suppose we're at the solution xk. And then we want to find a perturbation, delta x, that takes us closer to this, to this minimum. That's our goal. Start here, want to end up there. What we can do is take this function that we've got and kind of expand it and tailor it and have a local quadratic function, given by this dash line, and say, okay, at this particular point, my functional, I've got a local quadratic that I can work off that's got a derivative and second derivative. And I'm going to generate a local quadratic estimation of this that has 2 terms in the Taylor effect. And then what I want to do is to, with respect to this local quadratic function, find the minimum. So if I'm going to do that and try to find where to make this a minimum, then I end up with the following system. This is basically Newton's method, which says that my perturbation is obtained by solving the following problem. I look at the second derivative, that delta is equal to minus the gradient, or then rearrange it, I get delta x is equal to f prime over f double prime. So if you had a function f of x, you could go ahead and do this, and that would take you down to this particular point here. At that time, everything changes. The gradients are changing, curvature is changing, and so then begin anew, and start that, and hopefully get over this little hump here, and you gradually get down. So that's the sequence. So the good part about this is that we're going to be solving at each point a quadratic system, just like we had done before, except instead of getting the full solution up, we're just going to get a little curvature. So that's fine. The things, and especially if you're in this region in here, where you're kind of on track to get to that local minimum. But depending upon where you are, maybe second derivative is equal to 0, so that's actually going to provide a very large x. Or perhaps even if it's in the wrong direction, f prime, f double prime might have the correct sign, in which now you want to go this way, but you're going that way. So you have to do things to kind of guard against this. So if you have the wrong direction, you want to change the design, but if you have even the right direction, second derivative guard, then you're going to temper things back a bit. So the idea here is generally to solve for a perturbation, but then not necessarily accept the full perturbation. You've got to just say, okay, I think that's kind of in the right direction. I might scale it back by a certain amount. So the output xk plus 1 is equal to xk plus some proportionality of your delta x that you just solved for. And you can continue to do this with your additions for convergence, meaning that the derivative is maybe not 0, but less than some really small number, and that between two successive iterations, you're really not going anywhere, so that norm of delta x is less than some tolerance, and still need to keep track that the curvature is. So that's kind of the idea for a linear problem. We got a function like this, x prime or x star, or our solution, can be given by the same formula, and it's obtained in one step. For the nonlinear problem, we're going to do a sequence. We're going to start here, make perturbation, start there, make and we just keep cycling around on those quadratic optimizations, and we just iterate until we've converged. So the good thing about this is that all of the things that you kind of understand with respect to what we did this morning, is now just transportable over. And the only thing that's changed, instead of like finding the full solution, I'm just finding a perturbation. Okay, so what about multivariate functions? So that was like f of x, where x is just the same scalar. But really, if we got, well, for instance, in that toy, we've got m layers. So now we've got m parameters, or in the Crosswell. So one dimension, Crosswell, 1,000, 3D, 100,000. So now this now becomes a vector, and you want to find a solution that basically for the gradient in each of those directions. Now they're m. The gradient is equal to 0. Tolerance. So what do we do? Well, we can just do exactly the same thing that we had done for the single parameter, except now we have to make sure that we're doing it for each one. So this, what we're going to introduce is a gradient operator. So we're actually going to differentiate our objective function with respect to each of the parameters. So here we have So we've got, if we're at the solution f, we look for phi and phi. We're just doing Taylor's phi plus the gradient times delta plus second derivative times delta. So these are, you can see the similarity here. When we had a single variable, we just had x. Now we've got delta m. Here's the function. Here's the function. This is the derivative. Now it gets scaled. Multivariate function. And this is the second derivative. Now it gets scaled actually to a grab, which is it's called a Hessian. So this is the matrix. So the gradient is the vector, Hessian's matrix. So what does that look like? So the gradient looks like this. So it's the partial derivative of phi with respect to m1, m2, and 3, and 10. So that's That's a vector right now. And the Hessian is telling you how much the gradients change. So the Hessian is the gradient of, well, the derivative of the gradient. So it looks like this. So the first term is the second order derivative with respect to M1. And then this is with M2, and M1, M1, and then on. So this one here will be noted by the letter H for Hessian. This is an M by M matrix. And each element in that is the second order partial differential of phi with respect to Mi and Mj. Okay. Nothing particularly extraordinary. It's just you have more of the same stuff. And we're going to hit a minimum when the gradient is equal to 0. But now that means that each component of the gradient vector, so each component of that has to be equal to 0. And that H is positive. So how do we do this? Well, let's begin with the solution. Let's begin with M sub k, replicate the iteration. And then we're going to solve this matrix system, H delta M is equal to the minus the gradient. So this is exactly the same as we had before. So here is the one parameter, F prime prime delta X. So that's like H, okay, delta M, and then minus G, which is minus F prime. So the simple parts are identical. They just in one case, everything is a scalar, in the other case, we have vectors and matrices. So we solve this, and then we get a delta M, but just the same as we had before. We might want to scale it back. So we're going to be concerned. We think at least this is the right direction. Hold that. But it might be the wrong length, so let's just scale it back if we need. So here's the procedure that we're going to do. We're going to minimize this thing. So here's our misfit, and here is our model. So I've got rid of all the tangential complexity. Just like here's a small model. Okay. Now we take the gradient of that. So grad phi of this gives you something like this. So differentiate a forward modeling operator. And that is going to be something called sensitivity function, J. So J is going to be the gradient of a forward model. So Jij is the change in the basically the data with respect to the change in the J parameter. Okay, so that's a good thing. That's a good thing. So we got this cube of cells, and we got a data. Okay? And what we really want to know is if we change this cell value by a little bit, how much does that change? And in fact, from the point of view of fitting the data, and we want to know if we change this cell, what's the effect? This cell, so all of that is encapsulated. In the sensitivity component here. So remember data. I connects the data. Jij. So I connects. So this is the data. This to be like ij. And then J cycles through from 1 to M. So this is just the change in the data with respect to change the first cell, second, third. Okay, so that's J. The gradient is simply like this. It's J transpose times the difference between observed data plus data. Okay, so that's it. We've got the gradient at least. So what about the next derivative, the Hessian? Well, we've got to apply the gradient again. So the Hessian is is grad of the gradient. Now that actually carries through, it's got a couple of terms. One is J transpose J, but the other is how much that sensitivity is changing as a function of the model. And we're going to choose what we do just to neglect this term. It actually turns out to be a pretty reasonable approximation in a lot of cases. So we're going to use what's called a Gauss-Newton approximation and basically say that our Hessian is just J transpose J. So then here's our system. So we've got H delta M is equal to minus G. And H is J transpose J plus beta delta M is equal to the gradient here. And delta D is just the difference between the observed and the predicted data. So this should start to look pretty familiar, right? Because like, didn't we kind of do this earlier this morning? And we had a G transpose G plus beta. Right? So this is all kind of similar. The only thing that's different is that we're dealing with the sensitivity as opposed to the full operation. So just to flesh that out, when we did the linear problem this morning, we had a GM is equal to D. That gave us a G transpose G plus beta that is equal to this. Okay. Now we're going to do the nonlinear problem. So in this case, for perturbation, we have J transpose J. This equal to this together. So the thing is that in the localized problem, J kind of acts like an approximate forward model. In this case here, he was the forward model operator. Now here this is like an approximate forward model operator. So that's a good way to think about it too, is that if you're sitting at a particular place, you've got a local quadratic expectation, then you're going to, for finding perturbation, you're just going to J is being important. Okay, so how's that? So far, so good. How's that going to play out here when we do the inversion? We still want to normalize that, but we're going to have to initialize. So M naught, start model, and we'll start with the starting value of beta. There's still a Tikhonov curve here somehow, and we kind of want to be at there or close to it. So what I imagine the following: we started on and beta, and then we just do this. That I just talked about and try to find a solution to a minimum of that particular value of beta. So you can imagine going along that line. And then the next thing is you could let's change beta. We'll start with that model. We'll change beta. And now let's see along here. So you can imagine kind of successively doing that as you're going along here. So that's essentially what we're going to do. We're going to set up our Gauss equation, H delta minus G. We're going to solve that and update. When I say line, that means paying attention to whether or not alpha needs to be less than 1. And the other thing that we're going to do is something very expedient, and that is we're going to start with large beta, and then we're going to kind of cool down or solve the problem so that we land close to Tikhonov. Never going to change beta. We're going to change beta with a bit of cooling schedule. And we understand how that works. As I make data smaller, then I'm going to be getting data better. So why not set up procedure here. We start with a really big value argument, and then just gradually solve for a suite of problems with data. So this has got a lot of variants, but that's the essence of all of them. I mean, there's all kinds of things you can do as far as how you solve system of equations, cooling rate, and stuff like that. But I think for us at this point, this basically encapsulates how that nonlinear problem is going to solve. So just to summarize, we've got this system here. Here is our linear system, and here's our nonlinear system. And they're basically identical, except in here, we're going to iterate and solve for delta M. But that does mean that all of the intuition, all of the understanding that we had from the linear problem is completely valid here. Okay, so let's do something. Let's look at the DC resistivity problem. In DC resistivity, we're just concerned with either the resistivity rho or the reciprocal electrical conductivity. Electrical conductivity changes by many orders of magnitude, depending on the rocks. So actually, this top scale is resistivity, going from 10 to the minus 2 Siemens per meter, ohm meters, to 100,000 ohm meters at this time. So shield rocks or volcanic rocks tend to be up in this region in here. Massive sulfides, graphites, saltwater is really low resistivity. And a lot of the things we're often interested in, clays, shales, and stuff like that, have resistivities of 50, 100 ohm meters, something in that scale. The resistivity actually depends on a lot of things, and rock type, pore fluid, porosity, all kinds of things. But and then just varies a lot with different rocks. But the one thing about electrical resistivity or conductivity is that it has a large applications in many areas, and that's just one of the reasons so special about it. The basic resistivity experiment is as follows. So let's suppose that we've got this was actually something that emulated a mineral deposit. Okay. And it's got an over that's 12 ohm meters. There's a straw here that's 200 ohm meters. This is the mineralized zone. The top part of that's really resistant, so it's like 400. And then the yellow and the red are both really quite low resistivity. So that's kind of what we're up against. And now in the resistivity survey, we're going to put a current into the ground. We're going to do something like that. So the resistivity current, you take a generator and you hook it up into 2 probes to the ground. And so now we're going to get current flowing from positive end of the generator to negative. It's going to be flowing in the earth. And then the question is, where's the current going to flow? And then what kind of signal am I going to get? How do I understand this? So first of all, the current is going to go from here to here. So maybe I can ask, I'm going to give you 3 options. The current would just go like this. The current could go around like this, or the current could go in. Anybody want to suggest what we should go for? So 1 is geometry through, 2 is around, and 3 is without. So all people that did resistivity, what's going to happen? Silence is astounding. Go ahead. Yeah, put it on.
And then go for the 3 and then
And why?
was the low resistivity in the quantum.
Okay. And who would agree or disagree? Disagree. Okay. Oops. Yeah. So your intuition is right. So if this is, resistivity, if you put a big resistor in there, it's going to go around, right? So that means that current would ordinarily kind of go through there, but it's going to kind of go around the bottom. Yes. And then maybe get sucked into this region in here. So it's like kind of half of least resistance. Okay, it's sort of the easiest way. Okay, so that's good. So now we've got currents. We're going to measure the electric potentials. I mean, that's what we can measure, right? We can measure electric fields, right? So to do that, we need to have 2 probes and voltmeter. Fair enough. So that's what we're going to do. So again, people who have done DC resistivity, what's your understanding about where that voltage is coming from?
Depends on the geometry of the current electrode.
Right, so that's true. So here's our 2 current electrodes, and we're going to measure the voltages. But then the question is, what is really happening, or what are we measuring that's really sensitive to this bond? I mean, current. I mean, maybe it's the currents that are kind of flowing around, or I don't know, just what people do these days. I'm just trying to see how you intuitively understand what's going on in DC resistivity. Anybody? Oh my God, you got the quietest group. Okay. Okay, so a fundamental aspect of DC resistivity is that this is steady state. We're at 0 frequency, right? Steady state. So the currents have got some path that they're going, and they don't change. 1 minute, 2 minutes, 3 minutes, the currents just keep changing. So that means that the normal component of the current density that's going through in wherever you have a change in the conductivity, that has to be constant. And if you've got different regions of conductivity, and yet the normal component of current density has to be the same, because you've got so we've got current coming in here. These 2 are equal. So on the left-hand side, you've got sigma 1 E1 electric field. So this is Ohm's law, right? That has to be the same as what's on the left-hand side. So the physics of this is that you've got a constant current that's going through. So J, current density, is the same. But the conductivities are different. So that means that the electric field here is different from the electric field here. And that is not. Okay, how, you guys are all physics, this is great, because you guys are all physics guys. Okay, so how is it that I can have some kind of boundary at which the electric field changes discontinuous cost? Yeah. Capacitor. Not quite. Not quite. If I had it, how would that give me a chain of this? Anybody? First here, this. Anybody? How? I've got a situation, okay, in which somehow on one side, the electric field is different than the others. The reputation for a class is on the line here.
It has to do with how the charges distribute around the countries.
Perfect. So the only way that you can get a change in electric field, so if I have a positive charge here, right? Somehow I get a positive charge, right? Then what's the electric field in that? It's going to go up like this and like that, right? So that means that if I apply a background field on this, my field is, if the background field is pointing in this direction, my field at this positive charge is going to be reduced, and the field here is going to be increased. So there's going to be a change of the magnitude of the electric field. So the fact that E1 is not equal to E2 means there must be a charge. And that is the key physical understanding of resistivity. It's charged with power. So that's the next, so it returns up. So the fact that we've got currents that are flowing through here, and the normal current density has to be continuous, means that there's charges being built up. And if it flows from a resistor to a conductor, gives you negative charges. Conductor to resistor gives you positive charges. Okay, now we're one step closer. What's the final thing? How do we go from these charges to electric potential? Oh, come on. Oh, right. They forget the okay. So the undergrad. Come on, if I give you some charges, asking for electric potential, so do you. Coulomb's law, right? If I've got a charge anywhere, I can tell what the electric potential is away from there, just using Coulomb's law. So I got these charges built up, I can measure potentials, now I can use two probes difference. That's it. That's the DC resistivity experiment. Pump current into the ground, that current moves in such a way that establishes a steady state distribution of currents. There'll be charges that are built up in place where there's continuity, and those charges will give rise to potential. Okay, so that's the physics. Now how do we tackle this guy? Well, here's our basic equations. So at DC resistivity, maximum equations at zero frequency, we end up with div sigma grad phi is equal to current. So we're going to inject a current, and here's a delta function. So it just means we're injecting at a point. V is going to be the electric potential, and sigma is the electrical conductivity. So here is our equation that we want to solve. So we've got Ohm's law, J is equal to sigma E, and then E is equal to minus grad V, and then J dot N is going to be equal to 0 at our outside box. So we're going to make, we need to have a volume that's large enough so that all the currents die. So how do we do that? Well, we've got to take this equation and we've got to discretize it, we've got to put it on a mesh. So what we're going to use is a finite volume technique. And that means that we have cells and things are defined in different places. The electric potential is going to be defined, say, at the center of the cell, where it could also be defined on the nose. And we've got currents that are at the basis, it's a flux. And we're going to use a finite volume technique to discretize those equations so that we can take this and basically represent that in a matrix form that looks like this. So now G is a gradient operator. It's not that full operator before. G is a gradient. M is a mass matrix that depends upon the electrical conductivity, and G transpose is divergence, which is transpose gradient. So the forward modeling operator is just solving this matrix system with a Q on the right hand side. There should be a Q here. Another. We call that Q. Okay, our generically, let's just call our forward modeling matrix A. So A of M times Q, since we're going to be potentials, is equal to Q. So we got a source term, we got electric potentials, and we got a matrix to be solved. If we solve that, we will have found the electric potentials everywhere on cell centers or the nodes. So A was, notice this quantity A, it's basically composed of the gradient operator or its transpose. And so since it's a gradient, it's just like 0 everywhere except the plus and minus 1. You might expect that this is going to be sparse. And in fact, we'd be right to say that if you look at the matrix A, it's tend to be sparse, symmetric, positive, definite, and that means it's simple to store, and you can also use it more readily when you're actually trying to solve the problem. So our solution is basically solving this system here. And we have to solve it for each time we change our source location. So if we put it current here, we solve it. But each term, we solve things. So it's just like in a lot of problems, a lot of computation is involved in how many sources you actually have. So anyway, we call this forward problem. We can either use iterative solver or a direct solver. And here we are. So we've got an inverse problem. We want to solve this. We need to compute the matrix J. And now there's a question about, okay, how do we do that? That sensitivity matrix is perhaps a challenging thing to get. So let me just kind of walk you through at least the high level. I mean, we're not going to get into all the details, but you'll get the idea. And the idea and really important in how we go forward, not only on this problem, but on the other. So our forward modeling is this system here. And our data are going to be like the difference. So if we solve this gives us the electric potentials, let's say at each node. So we've got this great big grid, and then we solve it, and we've got the electric potential in each node. And then what we're going to have is the data is the difference between this node and here. So we need to, we've got a potential difference because we've got two ends of our voltage. So that means that it's going to be this minus. So in order to get the data, we need to have like a projection matrix that transfers the field from what we've solved for to the actual data. In this case, it's a potential difference. So that means that our projection matrix is going to be like a 1 minus 1. This is a 1 minus 1. So depending on where you go. So we've got, this is our system. We solve it. We get U, electric potentials everywhere. And our data are just some projection of those potentials. So now, how do you compute the sensitivity? And this, what I'm going to show you now, is completely generic, and you can use it in all kinds of problems. And for many problems, it's actually a must to be able to do that. Because the sensitivity matrix, if you think about it, is really big. And let's suppose you've got, even a data is not anything, but you've got a 3D problem. So let's look at a million cells. Okay. Now your sensitivity, for each data, involves a million elements, right? And if you've got 100 or 10,000, your sensitivity matrix could easily be 10,000 by a million. Right? It just happens really quickly. So we cannot store it. We can't store it. So we need something else. So something else we can do is find representation of the matrix J that is composed of the product of 3 other matrices. Well, so there's going to be a generalized matrix here. I'll explain just in a second. And here's A minus 1, so that's a forward modeling. And here's P, here's our projection. So we're actually going to try to form and store this. This is an operation, and that is a trivial sparse matrix. So in setting all this up, we want to find the change of the potential with respect to our model. We have this as our core volume. So we can just differentiate. Just use differentiate, use the chain rule. So on the first step, we're going to do derivative with respect to M. Let's fix U. So then that's just the chain of all of this with some fixed U. We'll call it T. And then plus A, and then to the chain of U with respect to all of elements. So we'll call this thing G. And then we're going to, if we differentiate the right hand side, we get 0. We got this. That gives rise then to this plus this is equal to 0. Or if we now reformulate that, so then rad mu is equal to minus this times A minus 1, which is that. So this decomposition is hugely critical in a lot of problems, especially where we're dealing with any kind of reasonable problem. So let's just kind of examine this. We've got the sensitivity for the DC problem. It turns out, so A, I said, was like this. M is some mass averaging matrix, and we can write P into this form. So to clear everything better, we're like this. So we got this quantity here, we can prove for. Now we're going to solve that. And now how do we solve? That's a big problem. We're going to use a quantity free algorithm. This is what I'm trying to make up here is use that y. Y is equal. But basically, in order to solve this system, we're going to multiply this matrix here onto the right-hand side. So this is just a vector, and then we need to multiply this quantity here onto a vector. And that means we need to be able to compute J times the vector, because J is an operating vector, and J transpose onto the vector. So those are the operations that we need to do. Remember, J was just like this, and all these matrices are sharps. So that means like, okay, we can do this. So we're going to use a concentrated solution, which is going to involve multiplying sensitivities on the vector, but we've got this representation for the sensitivities. Smart allows us to solve the problem. Okay, let's do an example. So here's the 2D VC resistivity problem. We've got a conductive block in here. We're going to use an array where we've got electric dipoles for current and potentials for receivers. And here's our apparent resistivity pseudo-section. So for each datum, we try to find a homogeneous half space that gives rise to that particular value of the datum. And so here's what the data. So you can see, so this is apparent resistivity, so red is low. That's good, kind of centered over here. Blue is high. So here's the data. Even from the data, you might get some idea that, well, I kind of think there's something there. But this is a very convoluted representation, so we need to inverse. And now I'm going to step you through those Gauss-Newton iterations. So here's the true model, here's the observed data, and here's our kind of economic curve. So at the first iteration, we're up here, we've got a very big misset and very small model norm. And here's the predictive model, so it's just kind of got a little bit of showing that and predictive. So that's the iteration one. Iteration 2, you can start to see it pull out a little bit more. And kind of starting to get the data for here. Iteration 3, see we're here, so starting to do a little bit better. And iteration 4, we're here, and iteration 5 here. So that's pretty good, right? So 5 iterations are observed and predicted data, and we'll come back to that. We've got a model that is in the right place, at the right depth. It's smooth at the edges, but our objective function was one where we're looking for a further small. So that's the procedure. I think it's worthwhile just kind of showing how this works then in real life. So I'll just take a couple minutes and show you a case history. This is a place in Australia. It's called Mount Isa, and there was the goal there was to try to find a conductive, potentially conductive mineral deposit in a region of siltstones and volcanics. The thing that we're looking for is a moderately good conductor. But if you look at all of the various rock units that are there, you find that there's some that are resistive. There's some that are, really, there's also one that's really conductive. And the thing that we're looking for is something in the middle. So the Mount Milford horizon has got a high conductivity, but there's something else that's got very high conductivity. There's a few that have moderate conductivity, and some that don't. So it's a bit of a mixed bag, but we're doing DC resistivity, and we're going to try to see what we find. So here's the data. So we've got a current electrode in here, and we're measuring potentials out here. We've got 10 lines of data, so we're just, this is the north-south, this is sort of 4 kilometers or 8 kilometers and 5 kilometers up here, and we're in 10 lines of data across here, and trying to see what we see. So this is the pseudo-section. You see the red is indicative of something that is conductive, so there's something there. If we change, and here's the thing that you always want to do, is you want to, if you cite a part from one direction to something, but if you cite it from the other direction, you might see something different. So you're always looking for different ways of citing the target. And yeah, you get another set of pseudosections that now look like this. So that's what you got. You got 20 of these pseudosections, and the question is, okay, can you find a 3D structure that's corresponding to that? So what we do is we take a mathematical cube, divide it into a whole bunch of cells, and then it deducts the value of cells through what I was talking about. And so you get something that is fitting the data and also has some structural continuity and doesn't have too much sphere. So what we're seeing now at this point is this is the result of the. We've taken it and we've done conversions, so we fitted all those pseudosections, right? And now we're looking at a 3D model. And then we want to test that model. So we're going to slice it in and out, for top and bottom, and then we're also going to rotate it around and change the iso surface. So at this particular point here, we kind of slice through. The red is indicating conductive material. Blue is resistive. So we get some things that are really conductive, some things that are really resistive, and stuff in the. So you can see there's this big conductor that's coming through there. I mean, we did see something on the pseudosections that indicated that there would be something there. But here, actually, now we see this very, very strong geologic feature that turns out to be this black shale unit. So that's sort of the end result. And this is kind of where you'd like to be, right? You'd like to go from physical data to some kind of something that looks a bit more geologic, and in fact, in this case, it's really quite successful at delineating this flat shale unit. It turned out that for this particular example, that's not exactly what was being sought from the point of view of mineralization. Turns out this guy in here is actually part of what we really want to get, but in order to find that, we need to use IP. How many people here have used IP or induced polarization? Do they talk about that in the undergraduate classes here? Do you like IP?
On a daily basis.
Yeah, so in this particular case here, there was a companion data set called induced polarization, and that actually turned out to be more diagnostic. But from the point of view of like a DC resistivity, this is actually been, I think, really quite a success story. We started off with, acquiring DC data. You go ahead and do this Gauss-Newton inversion that I was talking about, and come up with something that is. So, just in summary, then what we've done, we talked about the nonlinear problem. Looked at an example of how to discretize not only that DC problem, but any partial differential equation problem that you've got. The big thing being the sensitivities and how to carry out the optimization. So that's basically it. We've got that now takes us to the non-linear problem. There's two more things coming up. One is maybe looking at different kinds of norms as opposed to L2. And then I'll talk about field scale and then the future. So let's see how we do. So let's take a break. Again, special rates. Regroup. Okay.